Alright, so this talk is on symmetry and how it affects plasmonic molecules. So plasmonic molecules are pretty much just groupings of plasmons that interact with each other to form a nanostructure. And a plasmon is just the collective oscillations of the conductive electrons in a nanoparticle. These plasmons, or the electrons on them, can interact with an electric field like they do in an atom to form plasmonic states. And these individual plasmons can also interact with each other to form cluster states. And you can think of these as analogous to molecular orbitals, where these will have bonding and anti-bonding modes based on the distribution of the electrons on the surface of the plasmon. So in this specific study, they looked at a trimeric D3H silver nanoparticle cluster, and they wanted to view the effects of increasing the angles between two of the plasmons which will lower the symmetry of the molecule. So real quick, here's a just chart showing the kind of shape and dipole moments of these molecules. So the top half of the chart will show the anti-bonding modes, and the bottom half will show the bonding modes. And on the left, we start at the D3H completely symmetrical, pretty much equilateral triangles. And as we increase the angle between the two bottom plasmons, we break that symmetry and turn into the C2V group until finally we increase the angle by 180 degrees to 180 degrees at the D infinity H subgroup. So one thing to note though, we're only looking at the bonding modes in this talk, and the bottom half of the chart is the bonding ones, where we have two degenerate starting E' modes that break into an A1 and B2 subgroups. We also, as the lowest energy grouping in this study, we have the A'2, which also breaks into a B2 molecule. The A'2 molecule, though, is not optically active because it does not have a true dipole moment. It has this spherical dipole. So they took a scattering spectra of these trimers, where in the top, where we have three pretty much lines where we have green, blue, and red, where the green line represents the spectra taken with non-polarized light. The blue line has to do with transversely polarized light, and the transverse direction is simply the perpendicular to the direction or the base of the triangle. The red line, or the B2 grouping, is longitudinally polarized light, and that is in the base of the equilateral triangle, or parallel to the base. So the first spectra on the left is the doubly degenerate E' orbitals, where you only see those because they have the dipole moment. You can't see the A'2. But once we start splitting the angle between the bottom two, we break that symmetry or degeneracy and form the B2 and A1, where the A1 is blue shifted and the B2 is red shifted. And we can see that as we continue on till we're linear, the A1 will continuously be blue shifted, and also since it's becoming a higher energy state, the population will decrease, and we see the intensity decrease as well, where the B2 redshifts and the intensity increases until it becomes this optically active species for the D infinity H system. One of the things though that we can note is that this optically active linear species, it does not come from the B2 system from the E', it comes from the A'2. And one of the ways that we can know this is because the B2 system forms this the pi G state, which has no permanent dipole, so it is not active. But we can also support this in a second on a future slide. But real quick, this is just a chart or table that shows the same thing as the last tables. And on the top, pretty much table A shows the same thing, where we have wavelength versus the angle, and we can see the energy split again, where the A1 blues are blue shifted or lowered in wavelength, and the red are red shifted and increase. And the B is the theoretical calculations, and they match pretty well to the experimentals. And on the right, then, we have a ratio between the A1 to B2 population, or the intensities, and the ratio decreases because as the A1 becomes higher energy, it'll be less populated, so the intensity will decrease. So lastly, here we have just the energies of the system versus the angles. of each state, where once again the top half is the antibonding modes, the middle dotted line is the energy of just the free plasmon, and then the bottom half is the bonding ones. Where this is the one where we definitely know that the linearly actively optive species is coming from the A'2, is because when we look at the E', when it turns into B2, the energy continuously increases, but both theory and the experimental show that the B2 needs to be redshifted or decrease in energy, and the A2', when it turns into B2, does this. It just increases initially and then decreases to linear. So, just in conclusion, they looked at the energy levels of the plasmonic states, and that the visible B2 state comes from the A'2 mode instead of the degenerate E'.